start committee, particularly Vinod sir, even in this very little I know, I will share those ideas to you. Am I audible? Am I audible, ma'am?
Sorry, sir. Sorry for interruption. Your voice is breaking, sir. Still, voice is breaking,
I
sir.
think in make pressure and
I think
I'll
connectivity problem.
check for a better bandwidth.
Yes, sir. Yes, sir. That will
Am
be
I
better.
am I audible now? Yeah, you can
Yes, sir. Far better, sir.
make me presenter and mute the other people so that the other noise may not come.
Yes, sir.
And hope that the presentation is now visible.
Yes, sir, visible.
Yeah, thank you, ma'am. So the title is Introduction to Deep Learning by myself. Affiliation is Central University of Illinois. So I have nothing in my slides. I'll just keep writing and explain the things, whatever I know. And before we start, so I hope that all of you may have some sort of a basic idea of this artificial intelligence or machine learning and deep learning. But let us have a quick recap. So in the olden days, when programmable computers were first conceived, people really wondered whether such machines can become intelligent over 100 years of time. But today, the artificial intelligence, which is a thriving field with many practical applications and active research topics, prove that the machines are as equally intelligent as human beings. We look to intelligent software to automate understood or speech, images, or make some diagnosis in medicine and support some basic scientific and research. In the early days of artificial intelligence, this field was rapidly tackled and solved problems that are intellectually difficult for human beings, but relatively straightforward for computers. The problems that can be described by a list of formal mathematical rules and all. Later, when we try to solve some intuitive problems, the solutions allow the computers to learn from experience and understand the world in terms of hierarchy of concepts, with each concept defined in terms of its relation. Simpler, that relation mentioned in very simpler terms. So if we see a simple analogy between the different parts, different types of a learning and all, early success of artificial intelligence that took place in a very simple and formal environment, and it did not require computers to have much knowledge. Later, the major interest created when IBM's Deep Blue I think I have some problem with my pointer. Let me just wait for a minute. Session. What is this? One second, please. So, sorry for that small interruption. So, IBM's Deep Blue system that has actually defeated the world champion Gary Kasparov in 1997. So that helped, that also created a wave in the history of the artificial intelligence. And later, as the days progressed, there were so many other theories that evolved and make the artificial intelligence created lot of histories. Once the AI phenomenon has been done, later we have another subset of this artificial intelligence called machine learning has evolved, where the machine learning concepts basically has the roots in the AI, but they have a set of different algorithms have been defined that makes the machine to allow the computers to tackle problems that involves in the real world and all. So basically the performance, there are thousands of machine learning algorithms available. And later, we got deep learning, which is again a subset of this machine learning. So you might have seen a lot of diagrams like this, where AI is there, and in between you have a machine learning, like some sort of a diagrams like this, and you have a DL and all. So that clearly indicates that it is a subset of deep learning, subset of machine learning, and machine learning, subset of artificial intelligence. Okay. So in all these things, if you see the machine learning part alone, the performance of these machine learning algorithms depends heavily on the representation of the data. So what do you mean by this representation of the data? For example, when you have a logistic regression is there, one sort of classification algorithm called logistic regression. So when in the case of a logistic regression, which is basically derived from the linear regression, which is basically linear regression is basically meant for understanding or making some sort of estimation, and logistic regression making some sort of a classification. So in the case of a logistic regression, when this logistic regression is used to recommend certain, say, a particular classification for a binary classification you have done, then say, for example, a doctor tells the system several pieces of relevant information, such as presence or absence of some sort of a scar is present or not. So, if you have, let us say, for a patient, he has some sort of a scar present on his face or not. So what we can do is we can take some sort of features and try to make the logistic regression algorithm and see that the logistic regression will tell whether the person has a scar or not, whether it has scar or it has a no scar present on the face. So how this is happening is you have a human face, an image like thing, and say you have a human face like this, and he has a scar present over the forehead, and we are only looking at the scar, and we take from the image, we take the features, some sort of whatever the image processing features or computer vision features, you extract it, and from the features you give the machine learning model. So this machine learning model will input these features and gives the class or not. So this machine learning model is the logistic regression model, whatever you have developed. So the actual data is this, but the represented data is this, and this is what the representation of the data means. So if the same logistic regression, if it learns how these features of the patient correlate with the various outcomes, but it cannot influence the way the features are defined. It only look at these features, and then based on these features, it will develop a particular model. So this representation of the data, you have a lot of dependencies there. So this dependency on this representation is a general phenomena that appears throughout the computer science and every day of life. We have some data, but we are not bothered about the actual data in the actual domain. We try to represent it in some domain such that the computer science can understand that representation alone rather than the original representation and move ahead with that representation of the data. If it is applicable for not only logistic regression, any sort of machine learning algorithm, you take a support vector machine or you take a k-nearest neighbor, anything you take it, what the data is, whatever the data, you are trying to extract some features and then fit some model over that. So at that time, when you see the study of the neural networks, because for the deep learning, basically, which is an extension or a large sort of a neural network, we basically call the deep learning networks. So the artificial neural networks has become a prominent place for simulating the human brain. So the simplest and the first model of the artificial neural network is McCulloch-Pitts model. Which takes certain input and then try to so let us say it takes some input, some n inputs, xn inputs, and it tries to make a summation unit and an activation function. So this we call it as a a simple neuron. So each one has a certain weight associated with it. And then this will give some output y cap. So what happens here is you have the summation part. So the y cap is some sort of activation. So this is an activation function. You apply it on Z, where Z is x1 w1 plus x2 w2 plus and so on plus xn wn, or in short we write w transpose x. And this activation function defined as 1 if z is greater than or equal to some theta, 0 or if z is less than theta, where theta is some sort of a threshold parameter. Means it tries to convert this output into a binary value, either 0 or 1. This is what the simplest Makulov-Pitts neuron model. Later, there were different using this, people tried to solve some sort of problems like logical gates and all. Then like logical gates, if you see the logical and you have some inputs x1, x2 and y, and you can this basically the inputs looks like this and the output looks like this, and you can try to simulate a Makulov-Pitts neuron model to simulate this logical and similarly logical OR. So in all these things, if you try to make a plot between the input domain x1, x2, you have 0, 1 and 0, 1. So for 0, 0 it is 0 and 0, 1 it is 0 and 1, 0 it is 0 and 1, 1 you have 1. So you try to, so the neural network will try to draw a particular line, straight line called this, we call it as the discrimination equation or discriminant equation to represent this boundary. So with the help of this discriminant boundary, one can able to figure it out if the data lies between before this line, we can say that it belongs to this zone or this class, otherwise it belongs to the other class. So some sort of a discrimination will make it. So then there comes some problem called XOR, logical XOR, which is similar to this logical gate having two inputs, but the outputs, if you see, are something strange. So if you make a plot between this domain, x1, x2 domain, so 0, 0 is 0 and 1, 1 you have a 0 and here you have a 1 and here you have a 1. So you can't draw a line to separate this. So what are all the things which are separable? We call them as linearly separable data. And here you can't draw, if I draw a straight line here, then this point belongs to wrong classification. If I draw a line here, then this point belongs to a wrong input. So this set of data, we call it as linearly inseparable. So at that note, what to be done? There was a large gap came, and then you have a multi-layer perceptron has come, which helped to solve this XOR problem and all. So the multi-layer perceptron, if you look at it, the type of the architecture, we call it as a feed-forward architecture or feed-forward neural network. So where you have some inputs like this, let us say you have an input layer, and let me say I have some 4 neurons in a hidden layer, and let me say I have 1 neuron in the output layer. So this we call input layer, and this hidden, and this output. So the connections will be like from every neuron to every other neuron in the adjacent layer, you have these connections. So it looks like a connected graph like this. So all these connections are supported by certain weights, and you have similarly from hidden layer, you have these neurons and you get some output, let us say y. Your input vector, you give some x transpose or x, which is x1, x2, x3. You feed it to this and you get some output. So this sort of a layer, we call it as a feed-forward neural network or a typical multi-layer perceptron. So here what happens if at neuron J, if you take I have a neuron, let us say this is 3 layers, 3 neurons in the input layer, 4 neurons in the hidden layer, and 1 neuron in the output layer. So the topology, we call it as a 3-4-1 topology. Let us take some neuron J. So if I take some neuron here, what happens is I have this input vector x transpose, which is x1, x2, x3, some 3 inputs are in this network. And let me take here what happens at this neuron, all these having the weights, you have the weight vector, and that weight vector is going to do the summation of the products and then apply a activation function, and that summation of the products has been converted into some value, scalar value, and that will be passed to this particular input output neuron with some weight. So when you are getting a weight W output Y, this is basically, let's say these neurons outputs are calculated as, let us say this, whatever you have it are weights P, and this is the outputs H1, H2, say this is H1, H2, H3, H4. These are the outputs of these neurons. So H1 into P1, let us say my weight vector connecting these outputs of these neurons is P1, P2, P3, P4. So you get this is how you calculate this output here. And H1, if you take it, how do you calculate the H1? X1 into W1 plus X2 into W2 plus X3 into W3. You calculate it for H1. Similarly, for H2, you calculate, and H3 and H4, you calculate. So all these together, you get this output Y. And you have output, let us say Y cap, and you have the prediction actual output is Y. There is some loss that happens, and because you get some loss because the inputs of this complete functionality is dependent on the parameters, the weights. And these weights are basically initialized with some random values and because that are lying between 0 to 1. And so you get some error. Because of this error, you have some sort of difference between the actual and the predicted. And in order to correct that, you have this multi-layer perceptron supported with a backpropagation algorithm. That algorithm will help you to adjust the weights such that these weights will help you to get the correct output. And with that adjusted weights, we take the second pattern and make a forward pass. You get some error and then make a backward pass. So like this, you get different for all the inputs you get different errors and you get adjusting those weights, and finally you end up with that this entire process we call learning, the adjusting of the weights. At some point of time you get a fixed weights. That fixed weights, let us say the weights between input to the hidden layer is some sort of fixed weights, final weights W1, W2, W3, and the weights between hidden to the output layer vector P having P1, P2, P3, P4. So these weights are finally fixed that help that are able to understand and recognize all the patterns. With this thing, what we do is we take some sort of a test case and apply only one forward pass to check whether you get the prediction or not. This is how the entire neural networks concepts will proceed further, wherein you have one hidden layer, or you can have another hidden layer also. So you have one input layer and one hidden layer and another hidden layer and one output layer. So you have these connections, all connections from this input to hidden layer 1, and from hidden layer 1 to hidden layer 2, all sort of connections, and from the hidden layer 2 to the output layer, you have some sort of connections, and finally you get the output. So to what extent you can go is the problems at that particular period of time are very limited, and hence people could able to uh, find solutions using these neural networks with at most two hidden layers, or generally people stick to only one hidden layer. Okay. So at that point, is it clear up to this point, or if you have any queries, you can just ask me now. Or you can put it in the chat box also. Yeah, thank you, Suguna ma'am. Any queries? I think there are no queries, so I will try to further proceed to the actual topic, that is the deep learning. Further, I'll give some more concepts related to these neural networks. So I'll go back to the same XR problem once again. So in the XR problem, if we have seen just now in the X1, X2 space, so you have a 1 here and a 0 and a 1 here, 0, and this is the original x1, x2 space, where the XR is linearly inseparable. Now, what we do is we can try to apply some model directly to the original input to make it somewhat solvable. That is, what we do is we try to transform the input into some other domain such that you get, so you can have this 0, 1, 2. So this is H1, H2 space. So this is the transformed space. And here also you have a 0, 1. So the inputs, what we do is we try to transform these inputs, whatever you have, these inputs, the 4 patterns, we try to transform it into some feature space. So this is the original x1, x2 space. We try to transform it into some feature space by applying some kernel function, and because of that kernel function we could able to solve the XOR problem very efficiently. I'll just leave it as a puzzle for you to look at how this can be solved in the transformed space. So now come to the actual concept called deep learning. The word deep basically suggests an extensive part of learning. Extensive means you have a series, very exhaustive sort of a study. You are going to make it. That's why it is called deep learning. Means if you look at and why that's deep learning basically required is there are many reasons. First one, you have the data has been increased like anything. Means you have volumes of data available now. When you say volumes of data, don't you have such a voluminous data in the beginning? You do have that, but not this much volumes available. In the olden days, you have a limited amount of data only, we can say, but now you have volumes of the data available. So what? So when you have volumes of data, don't you use the same neural networks and make some classification or estimations? Can't you use it? It is basically not possible, because when you have large data, whatever the concepts like what we have seen, these neural networks, simple neural networks, or the same, these sort of networks are being used even for images for classification also. Like let us say, I have an image which is having the dimensions 1024 cross 1024. Means when I transform this image into a vector of all the pixels, this is roughly 10 cube and this is 10 cube. All the pixels is 10 power 6 cross 1. when I want to give it as an input to the neural network. And imagine 10 power 6 neurons in the almost 10 lakh neurons are present, and you have in the input layer, and you have a hidden layer. So when you have 10 power 6 neurons, at least you should have some sort of 10 power 3 to 10 power 4 neurons here to do the computations, and you get some output. That output, the neurons depends on the number of classes and all. Even for this data, you could able to solve the problems very efficiently using the neural networks. But such an image data, let us say you have these sort of 1024 cross 1024 images are available abundant, then also you could able to solve. But when you have lots of complexity and more and more images, if you make it the repository, then it becomes very huge. So the availability of the data is large. For small data, neural networks can perform better. For somewhat moderate portion of the data, if not small neural network, you can use some sort of a support vector machine or some other concepts to do the classification task. But when you have such a large data, then you need to have a big neural network. So when you have this, even if you increase this data set, let us say I have my data set, take ImageNet, you have so many data sets, large data sets you have it. Even then, if not a normal neural network, you can try with the support with the machine or something to do some binary classification on the input data. But even if your images are very high, large in number, then these support vector machines or any sort of other ensemble methods, whatever you use it, they can't do that. They will be heavily loaded and they can't even perform better. So once again, you have to come back to a large neural network. And why they can't do it? Because you have high computations are there. What do you mean by computation? If I want to do a one neuron, we have seen how much of processing is required here. Just for one output y dash, you have 4 multiplications and 3 additions are there. And in order to, so you have 4 products and 3 additions are involved here. So this is the first product, second product, third and fourth. And you see here, in order to get this, you have how many other products? You have 3 products and 2 additions for one hidden for H1. Similarly, for H2, H3, H4, all together you get 12 products and 8 additions are required at one to get this output. And your data set, let us say you have such a 3-dimensional vectors are thousands of input vectors are there, then imagine how many computations are there. Still it will work. But if your input rather than thousands of inputs, let us say trillions of input is there, then you can't do this work. Means when you have the data, not even millions, but billions and trillions and even higher volume of data is present, then having such a huge data, dealing with such a huge data, and where each data involves a lot many computations is not possible. And hence, you need to have some sort of a deep learning architectures required, because the first reason is the availability of the data. Second, increase of the computational power. So as the data is increasing, your computational power increases. And normal systems, let us say, even people nowadays use high-end workstations may not be sufficient to deal with such a huge computations. So what is required is you need to have powerful CPUs are required, or you need to have GPUs, or you need to have distributed computing systems required. Still, research is been flourishing in making these sort of architectural systems. Then what is the third thing is the algorithms. Creative algorithms have appeared that have completely changed the way neural network works. For example, in all these earlier neural networks, whatever the activation function I said, basically for complex problems, we use a sigmoidal activation function. So sigmoidal activation function is a little bit heavy, and it has some problem of a vanishing gradient problem. So you need to have some sort of a new activation functions, something like a simple function called a ReLU function and all is required. So with all these reasons, as the data is increasing and you need to have normal neural networks will not be sufficient. You need to have deep networks to solve such a large volumes of the data. So when you are dealing with such a large volumes of the data, then how to do these cost functions, loss functions is very important. So the basic difference, if you see, the loss function, it actually computes the error between the predicted value and the expected value of the output variable y. So this is basically the error between whatever you have, the absolute error, or you can say to avoid the sign changes, the squared error, you can say the loss function. But when you use this loss function over such a heavy network, this is once again a tedious task. So you need to define some sort of a cost function, a function that measures the performance of the machine learning model for a given set of data. So what the cost function will do is it will compute the error between predicted value and expected value averaged over the entire data set and represent it in the form of a single real number. So depending on the problem, the cost function can be formed in many different ways. For example, you take the loss function of the logistic regression. Don't worry about these terms and all. So where y is the expected value and y dash the predicted value. So if you look at this term very carefully, if y equal to 1, then this term will be eliminated. And if y equal to 0, this term will be eliminated. Means basically, if y equal to 1, you get a loss between y dash and y that is 1. You try to have the y dash biggest value is the largest value of the y dash is 1. If y equal to 0, then your loss function turns out to be like this. And we want 1 minus y dash to be the largest. means y dash to be smaller as smaller as possible, because it can only has one value. So the cost function of such a logistic regression, you can define it by combining these two equations, these two parts of this equation into a simple part. So these sort of small adjustments, we make it in the deep learning architectures. Another one, gradient descent. With gradient descent, you can see it as an algorithm with an iterative process, iterative algorithm that will try to find the local minima of a function. So again, the gradient descent, whether you could able to work it in this deep learning architectures, to what extent you can do is again you have to study. So all these things makes the deep learning looks like complex, but if we slowly look at every simple thing, you can easily understand that the how beautifully the deep learning architectures have been transformed the computations very efficiently. So so the main, whenever you are looking at the deep learning models, the three things what all required for you to understand is the activation functions, the parameters, and hyperparameters. These three are the most, you use a convolutional neural network, or you use a recurrent neural network, or you use a long short-term memory, or anything you use it. These three are the core portions of the deep learning. So what is, as we have already seen, activation function. Any sort of a neural network involves an activation function that will actually transform the some of the products happened at that particular neuron into a binary value, either 0 or 1, or a bipolar value that is either 1 or -1. So a linear activation function, if you take it, or let us say linear activation, basically these activation functions, you can call, have a two different activation functions, types of activation functions, linear and non-linear. Linear, we don't even bother to use, because in the real-time data, nothing is symmetric, and you can't have such a linear relationship. So you need to have a non-linear only. And the most common non-linear activation functions which uses are sigmoidal function, tan H function, and ReLU function. And sometimes leaky ReLU function also we use. So the sigmoidal function, if you take, it looks like this, having the data an S-shaped curve. So the sigmoidal function is basically 1 by 1 plus e power minus x, where whatever the sum of the products, you have it that is substituted in this variable, and try to get a solution that is a value lying between 0 to 1. So the advantage of this sort of a sigmoidal function, you get a smooth gradient, because you can see a very smooth S-shaped curve, and output values bound between 0 to 1, normalized. So the input is normalized to get an output between 0 to 1, and you can get clear prediction. But only problem in this sigmoidal function, for a large, for very high values or very low values of x, you don't get any change in the prediction. If x is increasing like anything, very large values, you don't get any prediction. Yes, Pavitra Naik, sir, does it give error value? Can you little elaborate what does error means here? you can switch on your mic and tell, or you can type it, difference between expected output and prediction. Yeah, see, what we do is you get the error, but it is not a one-time pass, right? You are going to, let me say, the input to the hidden, let us take a simple network only, and output. And my input is 3 neurons, same like what earlier we have seen. So what I do is I have let me say my input vector is x1, x2, x3 with this weights w1, w2. If I have a 4 neurons, so I have these weights. So this summation will get a h1, h2, h3, h4, and we have do this weights p1, p2, p3, p4. I get y cap, and y is there. And when you are getting h1, is h1 is it the summation of the product? No, because x1 into w1 plus x2 into w2 plus x3 into w3, you take it. So 3 neurons, and you have 4 x1, let us say you use this notation rather than this x1 into w11, let us say at neuron 1 in the hidden layer we are talking about. So h1 is basically x1 into, let us say this is w11 plus x2 into w21 plus x3 into w31, and this is you are applying activation function. So let us say this entire term is z, and the z is let us say this is z, and we are applying that activation function. So what I am doing is, if I apply a sigmoidal function, I am transforming it here. I am getting h1. So this is the intermediate nonlinear activation function I am using here. Similarly, I am using intermediate nonlinear activation functions. Let us say in all these things, I am using the sigmoidal function only. So when I calculate it here, so this h1 into p1 plus h2 into p2 plus h3 into p3 plus h4 into p4. Let us say this is some q, and I get y dash applying the like this. And this value we are trying to match it with the actual one. So the actual and this is the prediction happened. So you get some sort of difference between expected output and prediction. Naturally it happens because all these weights, when I start making this neural network learn, are randomly initialized, and so you get an error. Let us say I have some sort of 4 such a 3-dimensional input vectors are there. First input vector, I take it, made a pass, I get y cap, and I have the y, there is some error, and accordingly I will try to adjust these weights first, this p1, p2, p3, p4, and then I'll try to adjust these weights. And what I do is I will give the second input. With adjusted weights, I will try to do the second input. Again, I'll get error here. And again, based on the error, I will adjust these 4 kind of weights between this hidden and output, and these 3 weights between input and hidden. I adjust it, and I take the third input. Like this, first input adjustment, I am going to give it to the second input. Second input adjustments have been exposed to the third input, and third input adjustments have been exposed to the fourth input. Like this, once we do, at the end, the fourth input I have done, my input is over, but still my network is not learned. So what I do is I have this 1, 2, 3, 4, and after completion of these 4 inputs, we call it as one epoch. And once again, I will try to give this start cycling this process. Like this, I will do 1,000 times or even more number of times till this error between the actual and prediction for all these inputs becomes as minimal as possible. Okay. Did I answer your query, Pavitra Naik, sir? Yeah, thank you. So similarly, tan h function, if you take it, the tan h function will go like this, where you have e power x minus e power minus x by e power x plus e power minus x. So in this sort of tan h, the advantage is the output is zero centered. So almost it is similar to the say a sigmoidal function, and disadvantages also you have the same thing. Means if the x is having very high values, for any 2 successive high values of x, the output of this will not change. Similarly, for any low values of x, the output will not change. That is what the actual vanishing gradient we call. Then the most important in the deep learning, ReLU function. So that looks like this. You have something like this and go, which is defined very easily. A ReLU function that is basically maximum of 0, z, the y output equal to max of 0 and z, where z is the whatever that summation of the products you can see. The advantage here is it is computationally efficient because it allows the iterations to converge very quickly. And non-linear, it looks like a linear function, but it is not non-linear function. It is a non-linear because ReLU has a derivative function and that allows for the back propagation. The disadvantage is when inputs approach to 0, means if the z is approaching towards 0 or negative, then the gradient becomes 0. Then in that case, the network will not perform any sort of a learning. Means it actually, literally, there is no learning happens. But if you have such a problem, then you can go for this leaky ReLU function that looks like this. Where you can say y, you can maximum of rather than 0 comma z, you can say 0.01 times of z and z. So you can say this function, you can use it rather than, so this function we call it as a leaky ReLU, particularly when your z is approaching towards 0. Yeah, and we have one more. Which activation function is best for lung disease detection? See, these activation functions do not depend on the problem basically. They are simple statistical functions. What we need to look at is which function is trying to give better values or converge more easily, only we are going to look at it. And generally, you can rely on ReLU function as long as your input is not approaching towards 0. You can rely on the ReLU function. So after these activation functions, the next one is the parameters. What is the basic difference between parameters and hyperparameters also we'll see. So better choice of these activation functions, basically as someone asked for lung detection or some other detection, what is required for the machine learning expert is you need to understand the problem very efficiently, because different activation functions will work or behave differently at different times. Okay, so one has to understand the problem very efficiently, then only you can choose the activation functions properly. Then come to the parameters. Basically the parameters are randomly initialized. Why initial weights with small random numbers? But they're particularly randomly initialized, and we'll try to normalize the values between 0 to 1. And why we need these small values? Because when you are applying the activation functions, particularly like sigmoid or tan h function, if the weight is very large, you are most likely to end up possibly your training will never get converged. Okay, so we always try to have means your inputs may be normalized, and if your weights are not normalized, then there won't be any correlation between the input vector and the weight vector. So since basically in this neural networks or in deep learning, the inputs we try to normalize it, so as the case with the weights also. Then what is the difference? What is parameter and what is a hyperparameter? You have two different terms. So when you say parameter, what we mean is you have a model parameters. These are the parameters in the model itself that must be determined using the training data set. These are the fitted parameters. Hyperparameters means basically these are adjustable parameters. They can be tuned in order to obtain a model with optimal performance. Suppose if you take a neural network model I am using. So parameters of a neural network model are basically what? Weights. And if you are using the bias inputs also, then the bias weights also. Whereas hyperparameters is like learning rate, number of iterations, how many times I have to do the epochs, how many number of hidden layers I need to have, and in each layer how many number of hidden neurons are required, and choice of your activation functions. And if you look at all these parameters, they are hyperparameters because I can change my learning rate so that I can get different performances. This is adjustable. I can increase or decrease my number of iterations to see the neural network to what extent it is going to converge. I can increase the hidden layers as much as possible or as low as possible. I can increase the number of neurons in every hidden layer, or I can reduce the number of neurons in every hidden layer. Then I can have a try with the different activation functions. So all these things basically adjustable and will optimize the performance of the model. Whereas model parameters, weights which are fixed. So those things will not be much changing in nature. So one can think of differentiate between parameter and a hyperparameter. So hyperparameters will play a crucial role in the case of a deep learning. Yeah, we have something in the chart. What is the learning rate? Okay. Basically, learning rate is we can say step size. The amount that the weights are updated during training. When you are using, I have given only the skeletal view of this multi-layer perceptron and all. When you are using the back propagation algorithm, when you are using it here, yeah, when you are training it, when you are adjusting the weights, I said simply adjust the weights based on this error, and that adjustment of the weights involves a parameter called alpha. Okay. So that will be, you can basically, people use 0.01 or 0.001, some value like this for the learning rate, that will try to do a step decrement or step increment in the weights. Why that parameter is required is, let us take some sort of a convex surface like this, and you are at this position here, and you need to, your task is you need to approach the local minimum function, local minimum value here. So when you start looking here, you try to update the weights. If the updation is, I request the participant to mute your mic. So this will try to okay, when your updation of the weights is not controlled, then what happens is the learning becomes zigzag, and you may get a converge to this point, or it may kick back to this point again and come here, this and go. Like this it will do. Means the weights, you need to have some, the fixed local minima you need to reach, but when your controlling of the weights has not been done properly, then you may have this the convergence problem, you may not converge it. So this learning rate, for when you start here, rather than control it to approach it to local value, this sort of a controlling is done by the learning rate alpha. Is that clear, Vishalini Subramanian sir? Yeah. So these are the hyperparameters. So which are adjustable, and you can try a trial and error basis on these values to look at or to optimize the performance of your model. Either your model is a convolutional neural network or a simple artificial neural network or a support vector machine or anything. If you differentiate the parameters and the hyperparameters, parameters are basically fixed and fitted values, and hyperparameters you can play with to improve the performance of the model in an optimal way. Then you can have different types of deep learning neural networks. Most regularly used one is a convolutional neural networks, and you have a recurrent neural networks, you have a variational auto encoders, you have a LSTMs, and you have a generative adversarial networks, and so on. We can have varieties of neural networks, and each and every particular architecture has its own advantages and disadvantages. And beyond these things, what is important for you is regularization for deep learning. This is most important. Means the central problem in the machine learning is how to make an algorithm that will perform well, not just on the training data, but also on the new inputs. So many strategies used in machine learning are explicitly designed to reduce the error in the test cases. So the word regularization means any modification you make it to a learning algorithm that is intended to reduce the generalization error but not training error. There are many regularization strategies are there. So focusing on regularization is also equally important for any deep learning problem, particularly since the deep learning is that learning rate will be adjusted based on what technique or random. It is random. There is no hardcore rule to fix the learning rate value. You can initialize it randomly. Is that clear? So what the research in this sort of a networks is particularly one thing you should understand is this deep learning. Yeah, even you can have the value like this also. Okay. So all these models, when you see uh, the research in these, the difference between local and global. Yeah, 1 second, I'll come back. I'll come to that. So each and every type of these networks has a different purpose, but more or less all these are basically meant for image data as well as video data, or to some extent you can use signal data, one-dimensional signal, because in images and videos only you can generate voluminous amount of data. And just because deep learning is crazy, you should not use deep learning for simple toy problems unless and until you have very trillions of the data or more than that data, you should not use it. And this has made a revolution basically because prior to deep learning, people tried to extract the features from the images to do the classification task or recognition task. And everyone will claim using these features, they will try to fit a model and claim that their features are the superior or the best and all. So what deep learning will do is you don't extract the features. For the deep learning model, we just try to give the image and this deep learning model will extract the features. Wait for some time. And then you do the classification or recognition. Okay. So you can see trillions of papers in this domain where people extract the features and claim that their features are the best. Whereas one naturally people are fed up with this sort of papers because they are problem oriented, data set oriented. If I change the data set, those features will not work. Rather than they work properly, they will give disaster results and all. So deep learning has put a full stop to such a papers, and because the deep learning involves automatic extraction of the features. What features are relevant for an image will be looked by the architecture, these architectures itself. So means when you give an image as a raw image input, this is going to look at this image in all possible ways to extract where and all in which nook and corner you have good information, and extract that and then use those features and try to fit the model and do the classification and recognition. Yeah. So coming back to the question, uh, local minima and global minima. Let us say you have some sort of a convex function, a loss function, something like this. It goes like this. And when you are at some point here, so this is the global minimum point. But when you basically be at this position, when any sort of a gradient descent algorithm you use it, it will try to converge when you get this position. Okay, you can't, even if you can't go further. This is the problem, but still you can't reach this place. So this is the local minima, and this is the global minima. Reaching global minima is very difficult, but reaching local minima is easy. Okay, that something better than staying here is not advisable. Means you are not converging your weights. So you try to means by adjusting the weights, you are trying to minimize your local error to the possible extent and be happy with that. And why you are here? Because of the random initialization. Rather, if you are here, your random initialization of weights has put you here, then you may get here. But occurring of such an event is very trivial. So if you are lucky enough, you reach the global minima. Otherwise, you reach some minima, that is where the point at which it is converging, you stop your learning. So I just gave a very uh, very skeletal view, because most of the presentations, if you look at on deep learning, image and the diagram, I use the skills of deep learning. Hope that it is understandable for all of you, and if you have any queries, please. Yeah, I'm not written. So email ID is Chandramouli at utm.ac.in. So, do you have any queries? Not CATN, CUTN, Central University. You type it here.
If you have any queries, you can ask now. Participants can unmute and ask the questions. If they have any queries.
Morning, sir.
Yes, please.
Hello. Yeah.
Yeah.
Sir, for the basic implementation of deep learning for the project like in images, if we're working on images, which platform is basically best suited? If we have a lots of images, then what we have to pick?
See, even if you have a GPU system to implement deep learning architectures, normal systems will not converge at all. Okay, you need to have a GPU, or you can try at the beginner stage. You can use Google Colab. Okay, to some extent, because even if you are dealing with images of 32 cross 32, which is basically very small image, will not complete its learning part alone. Okay, so you need to have heavy computations. That is, particularly you need to have a GPU required. When you have a GPU using Keras or TensorFlow in the TensorFlow environment, using Keras or another Python libraries, you can work on this for these deep learning implementations.
Yes, any queries? Any other questions from participant side? Okay. So I think no more questions from participants. And there are no questions in chat window as well. I think we are at the end of the session.
Yeah.
I thank Dr. Chandramouli sir for sharing his insight on the introduction to deep learning, also providing applicability of technology in various sectors. So I thank you so much for accepting our invitation, sir, and getting associated with this FTP. It was an excellent and informative talk on deep learning, and we look forward to more such associations with you again, sir. Thank you very much, sir.
Yeah, thank you. Since I have only 1.5 hour time, I thought something put it in a different way than the regular other persons. So I use this sort of writing way of mode of delivering the session, so that even if 0.1%, if you get a new point from this session, and my purpose of delivering this would have been solved. So with this and note, I thank you once again, the organizers, for giving me an opportunity to have an interaction with all of you. Thank you very much.
Thank you, Chandramouli sir, for accepting.
Thank you, sir.
We will meet in next occasion. Good occasion.
Sure.
Thank you.
Yeah. Thank you.
So next session, that is second session of the day, starts exactly at 11:30 a.m. So we will join for the session at 11:30. Thank you all. Thank you.